In this video, we're going to take a look at section 2.4, continuity and one-sided limits and what those things mean. Here's a graph with a bunch of examples. And you can see a lot of these graphs that we're going to be working with are broken, and we're going to describe those breaks in the graphs. In class, we will do this exploration about talking about what is an interval. Intervals are really important when we're talking about discontinuities, because if we're looking at a specific interval, that's the only part of that graph that we need to look at. So what are different types of continuities? Let's look at some examples here. All right, so if we have different, one continuity here, let's say our intervals from A to B, A to B, and there's this part C in between. So if you have a graph that goes from A to C to B, something like this, right? Where the function at that point is not defined. So at that point, so you would say f of C is not defined. All right, so this discontinuous at that point because there's no y value. Even though the limit exists, there's no y value. Let's take another example. Again, A, C, B. So now what if you have something that goes on like this? Right, at C. Again, we're focused only at C. That's really all that we're looking at. You notice it has a y value right there. F of C exists, but the one-handed limits don't exist. So the two-sided limits don't exist. Okay, and we'll look at that again here in a bit. But then your third one that we're going to look at is if you have a function similar to the first, right? That looks similar to the first one, but point C is right there. So f of C exists, and your limits are even the same. But your limits and your function, they don't equal each other. Okay? So we're going to look at those three types of discontinuities, and we're going to list them right here below. The first one is where f of C is not defined. And we did that example up here, right there, where it's not defined. Number two, let me get the right color. Number two, the limit of f of x fails to exist. Right? And that would be an example right here. And that is because the limit from the left and the limit from the right, we're going to call those the one-sided limits, are not equal. Okay? And the third way, looking right here, you notice the one-sided limits are equal. However, the limit does not equal the value at that point. And the value is denoted as f of C. So we'll put that in there. Okay, so you have the limits as x approaches C does not equal the value at that point. So that's the third way. And again, that's this third option down here. So we'll draw a line. That's the third way that a limit could fail to exist. Okay, make sure you get all that down and understand those three ways where it could not exist. And then everything opposite would be true where it could exist. So it could exist, if the limits from the left and the right are equal to the value. It could exist if f of c exists and the two one-sided limits exist as well. So now let's look at the definition of continuity in the green there. It says a function f of x is continuous at a point c if the following three conditions are met. So the three conditions have to be met. Number one, f of c is defined. So like up here, in the first one, f of c was not defined. The limit exists. On the second one up here, the limit did not exist. And then the limit is equal to the value. So in the third part, the limit was not equal to the value. So up here we looked at when it is not continuous. This is defining when it is continuous. And so looking at here in the red, this is just a statement just summing everything up. It says a function is continuous on an open interval. So a function is continuous on an open interval AB. So that would be, we went from A to B, A to B, A to B, right? You're studying that function only from A to B. If it is continuous at each point on that interval. So every single point on the interval, it has to be continuous. The limits have to equal each other. There has to be a C value. And the limits have to equal that C value. So those three things have to happen in order for it to be continuous. Looking at removable and non-removable. For removable, let's say we have a function, right? So all right, we have a function there. Now there's this hole in the graph where we can actually replace that hole either where the limits are or elsewhere, okay? And then non-removable, right? So this would be like a hole in the graph. That would be a removable because you can always do a piecewise function and plug that hole anywhere on that graph if you needed to. But this one is non-removable. That's where your limits are not the same, right? So in this case, the limits as x approaches c does not exist. Okay, it does not exist. That's an example of a non-removable. And then you have on your intervals. So again, we're looking at our open intervals from A to B, from A to B, at this point C. C is the point where we're studying on that graph. So go ahead and try these. I just want you to sketch the graph, use your graphing calculator, sketch it on there, and then discuss the continuity. And you're looking at, is it removable? What kind of discontinuity is it? Is it continuous? Just answering all of those different questions about each one of these graphs. So pause the video, go ahead and try these on your own, and then come back and see how you did. So let's take a look at the first one here. 1 over x, I sketched the graph for us here, and you notice that it is broken. So right here, right, there is a discontinuity, and that means it's a non-removable discontinuity because you can't remove it. And it occurs at x equals 0. Right, so a lot of times we can define, well, all the time we can define a discontinuity as if you can't trace a graph without picking up your pen or pencil, it's discontinuous. Then you just have to define what kind of discontinuity it is. Like on B, it looks like, if you sketch it on a graphing calculator, it looks like it's continuous, but remember, if you plug in 1 down here, you get 0. So at x equals 1, there is that hole. So that is a removable discontinuity. And that occurs at x equals 1. Okay, so that's a removable discontinuity. And then on this one down here, this is a piecewise function. where on this first part is your x plus 1, and that's everywhere where x is less than or equal to 0. So there is not a hole there. It equals that point at that point. And on the second one, that's x squared plus 1. So the limits are the same because at 0, they both equal 1. And you can double check that here. When you plug in h of 0 here, it's 0 plus 1, that equals 1. Then 0 squared plus 1, that equals 1. That means, 1. Means their y values are the same, means it is continuous. So in that case, it is continuous everywhere. We'll say on the entire domain. Okay. And the last one is also true. This one is also continuous on the entire domain. And now let's take a look at this idea of one-sided limits. So imagine on a graph, you have this point C. Okay, and let's say this is our graph, whatever it might look like. And you're looking at the one-sided limits. If it's the limit from the right, that means you're coming from the right to that point, and you're studying the y value. Okay, it's as x approaches, but it's always the y value. So limits, when you're looking at that, you're looking at as x approaches this, what is your y value? So the same is true over here. If you're coming from the left at this point C, that would be coming from this side. And as we learned earlier, when graphs are broken, right, like this one up here, the limits from the left and the right are not the same, then that would be a discontinuity. Okay? And then the overall limit, in order for the limit to exist, so let's write this out here, right on the limit as the left. So it would be the limit as x approaches C from the right. And we would write that as limit as x approaches C from the right. And this one would be the limit as x approaches C from the left. And we would read that just as I said, limit as x approaches C from the left. And then our overall limit, we're looking at both of them. So here is our graph. We have our point C. And you notice your limits from the right and left are the same. And in order for the limit as x approaches C to exist, it has to be that this limit as x approaches C from the right has to equal the limit as x approaches C from the left. And also there has to be a value at that point. So this also has to equal f of C. So in order for that overall limit to exist, these three things have to happen. The left and right hand limits have to equal, and the value at that point has to equal the left and right hand limits. Okay? So in order for the overall limit to exist, all three of these things have to be true. Let's take a look at an example. Find the limit of f of x as it equals the square root of 4 minus x squared as x approaches -2 from the right. You can use a graphing calculator if you want to, whatever method you want. Go ahead and try this on your own. Sketch the graph. Limits are super important if we see them visually, so sketch the graph and kind of see if it makes sense to you. Pause the video, try this one on your own, and then come back. All right, so if we write it out, it looks something like this. The limit as x approaches -2 from the right of your function. And again, we're approaching from the right. So we're coming in this direction right here. And you can see that our y values are approaching 0. So our answer here is going to be 0. You notice it doesn't even exist from the left, but the limit from the right does exist. All right, so the greatest integer function, this is like a stair function. This is or a ceiling function, so to speak. Go ahead. I don't know if our graphing calculators, I'm not familiar with whether or not our graphing calculators can graph these greatest integer functions, but if you have seen these in the past, go ahead and graph them, and then we'll take a look at these limits. So this is what the greatest integer function looks like. And the best application I can think of is a parking garage, right? Where it's $10 per hour. So if they're there for 2.5 hours, it's still going to be that, for example, that $10 or that $10. But if you're there for exactly 2 hours, it jumps to the next level, right? Because it's open here. So it jumps right there. So 2 hours, it's going to go jump right to the next level. And then at 3 hours, it jumps to the next level. At 4 hours, it jumps to the next level. Okay? So you have the closed circles here, and then the open circles over here. All right. So now, looking at the limit as x approaches 0 from the right, left, and overall. The limit as x approaches 0 from the right, so we're looking at it here, that is equal to 0. So from the right, it's 0. From the left, now we're looking at it approaching this direction, and you notice it's actually -1. So from the left is -1, and then this one is asking about the overall limit. In order for the overall limit to even exist, the left and right hand limits have to be the same. Since these are not equal, then this does not exist. Okay, so this implies that this is non-existent. Okay, so that's an example of when the function, the left and right hand limits don't exist, the overall limit is non-existent either. So if we look at the continuity of this function, so I sketched it here, it's a half circle, and we're discussing the continuity. You notice it's continuous everywhere except -1 and 1. So if we look at the limit as x approaches 1, for example, from the left, that's equal to 0. The limit as x approaches -1 from the right, that's equal to 0. Okay. Now, like I mentioned earlier, the importance of the interval. So if we look at this function on the interval from -1 to 1, okay, only from -1 to 1, and that's the closed interval, it is continuous. If you look anywhere outside of that, which it doesn't even exist, because remember, it's a circle, right? It's going to be continuous, but it doesn't exist. So we would say that this is continuous on that closed interval of -1 to 1. There we go. Okay. So even though it doesn't look like it, this is continuous because it has to be put in that closed interval because it doesn't exist anywhere outside of that interval. So some functions are tricky. You just have to think a little bit more about them. And again, the interval is important. Sometimes it might have to be defined in order to answer the question. So now if we look further into properties of continuity, and we've seen this before in this chapter, we've seen them before in other areas of mathematics, studies of mathematics. The great thing about math is it's a story where everything links together. Right here, we're looking at properties that we've looked at before in different contexts, and notice the same things are true, nothing changes. Right, we've seen the scalar multiplication, the scalar multiple, the idea of a product, if we multiply two functions, then it still remains true. In this case, it still remains continuous. So if we read what's up in the red text, it says, if b is a real number and f and g are continuous. So we've already established that the function f and the function g are continuous at this point c. Whatever that point is, they're continuous, right? So then the following are also continuous at c. Again, f and g both have the limits, the one-sided limits exist, and the value at that point exists. We've determined that already. Then we know if we multiply either one of those functions by a constant real number, that too is going to be continuous. If we add or subtract the functions together, then that function we get from adding them together will also be continuous. If we multiply them together, that new function will also be continuous. If we divide them, that function, given g is not equal to 0, that new function will also be continuous. All right, so again, this looks very familiar. It should look very familiar to you. Just pause the video if you need to get these down so that they're in your notes. So on this next set of examples, you're using the fact that each one of these are continuous on their domains to answer the questions below using the properties above, right? So for example, on number 1, and that's probably the easiest one, so you're welcome, you have x plus sine of x. X I know is continuous, sine of x I know is continuous, and because of the sum and difference rule up here, meaning if I add two continuous functions, my resulting function is also continuous, I know that that too is continuous, right? So if I add two continuous functions, right, and it's asking, how do you know each of the following functions are continuous? And I would put my reasoning there. So go ahead and do 2, 3, and 4, stating how you know that is continuous, if it is, and then come back to the video. Okay, so let's see how we did. So on the first one, when you add them together, we know that it's continuous. We talked about that one. Here you have a whole number multiplied by a function we know to be continuous. That's a scalar multiple. And then you have two functions we know are continuous being divided, and that is the quotient rule above. So yes, all three of those are continuous. The problem is number 4, right? Because yes, it looks like, if you look in here, okay, yes, scalar multiple there, function plus 1, then the function minus 2 divided by another function we know to be continuous when x is not equal to 0. It all looks fine. However, inside, because you have inside your cosine, you have a sine of x plus 1. That's a composite function. We haven't talked about composite functions yet. So down here, it says all composite functions are also continuous if their other functions are continuous. So if you look up here, we know that cosine is continuous. We know that sine is continuous. We know that x is continuous. And down here, 2x is continuous because the 2 is just your scalar multiple. So in number 4, because composite functions are continuous, if those functions that are put inside of them are also continuous, this one we know is as well. And you got a little bit of every. You got the scalar going here, the scalar going here, the addition subtraction here, quotient. So I think you have everything except for the product rule happening on number 4. Okay, so get this down. All composite functions are also continuous. And then let's look at the intermediate value theorem and what that means. The intermediate value theorem is just an existence theorem. It's a theorem of continuity. Now, it is logic, it is common sense put into words that sounds very confusing. So I'm just going to read what it says to you first, and then we'll kind of go over what does it mean. So it says if a function is continuous on the closed interval of a to b. So here's our closed interval, a to b. F of a and f of b are not equal. that means the y values are not the same. So on my graph over here, you notice a and b have different y values. And k is any number between f of a and f of b. So k represents any value between f of a and f of b. Now, between f of a and f of b, that could be tricky. In this case, it's only these values. Whoops, let me do it in green. It's only these values here, because my f of a is 0 and my f of b is looks like 2 or something, whatever it might be, right? So we're only looking at those values highlighted in green. Then there is at least one value of c in that interval such that the y value is equal to k. Now, what this is saying is k could be any number. It doesn't have to be on the graph. It can be any number. But c, f of c, has to be on that graph. Okay? And this shows that in order for this to happen, it has to be continuous. So every point that I highlighted in green has to exist. That's what this existence theorem is saying. Again, it's common sense put in terms that is pretty confusing, right? But that's what the intermediate value theorem says. So in our example here, it says show that f of x is equal to x to the third plus 2x minus 1 has 1, 0 somewhere on the interval from 0 to 1. So the first thing we're going to do is figure out, okay, what are our y values? This would be the f of a and f of b, right? This would be our interval from a to b. So we have to figure out what f of a is, which is in this case f of 0. And figure out what f of b is, in this case, f of 1. So when we do that, plug it in there, you'd have 0 to the third plus 2 times 0 minus 1. So this is all equal to negative 1. When you plug 1 in there, you'd have 1 to the third plus 2 times 1 minus 1. And all of that together equals 2. Now, what this does is it tells us the y values. They go from negative 1 to 2. Okay, so let's write that down. Y values on this interval of 0, 1 go from negative 1 to 2. And so it must have at some point gone through y equals 0. Right? It had to go through y equals 0. There's no way for it to go from negative 1 to positive 2 if it's continuous without going through 0. So the y values in 0 go from negative 1 to negative 2. Therefore, because of the mean value theorem, it must have gone through f of, no, not f of 0, sorry, y equals 0. Two different things. That's a y equals 0 at some point since we know that f of x is continuous. Again, it's common sense, but that just shows the importance of knowing that a function is continuous in order to assume that other points on that line must exist. Okay, so that's the mean value theorem. And that is it for these notes. Okay, so in these notes, we talked about continuity and one-sided limits. Thank you for listening.